The Laplacian-Former technique is designed to enhance the capabilities of vision transformers in capturing high-frequency components of images, crucial for effective semantic segmentation tasks. It utilizes a dual attention mechanism, comprising efficient attention and frequency attention, to adaptively recalibrate the frequency information in a Laplacian pyramid. This approach selectively intensifies the contribution of shape and texture features while reducing the complexity of self-attention to linear. Additionally, an efficient enhancement multiscale bridge transfers spatial information from the encoder to the decoder, preserving fundamental features. The efficacy of Laplacian-Former is demonstrated on multi-organ and skin lesion segmentation tasks, showing significant improvements compared to state-of-the-art approaches. The evolution of deep learning models in computer vision has led to the rise of transformer-based models, such as vision transformers, VIT, which have shown promising results in various tasks. The key to their success lies in their ability to model global semantic interactions through multi-head self-attention, MSA, blocks. However, these models struggle to capture high-frequency components of images, essential for detecting local textures in diagnostic and prognostic tasks. To address this limitation, researchers have proposed integrating CNN and VIT features using complementary methods. This fusion aims to leverage the strengths of both models to compensate for any shortcomings in local representation. Examples include Trans-U-Net, which uses a CNN-based encoder and a transformer-based decoder for 3D medical image segmentation, and High-Former, which combines a SWIN transformer module with a CNN-based encoder to generate multi-scale feature representations. Other approaches involve redesigning the self-attention mechanism within pure transformer models to enhance local feature representation. SWIN-U-Net utilizes a linear computational complexity SWIN transformer block in a U-shaped structure as a multi-scale backbone, while MIS-Former applies a non-invertible downsampling operation on input blocks to reduce parameters. D-Former is a pure transformer-based pipeline that comprises a double attention mechanism to enhance local feature representation. Despite these advances, limitations persist, including computational inefficiency, the requirement of a heavy CNN backbone, and the lack of consideration for multiscale information. These limitations have resulted in less effective network learning results in the field of medical image segmentation. The need for further research is highlighted to overcome these challenges and improve the performance of transformer-based models in capturing local and global features effectively. The paper addresses the limitations of traditional self-attention mechanisms in tasks such as tumor detection and cancer type identification, highlighting their tendency to overlook high-frequency information like texture and edge details. It proposes the Laplacian-Former, which includes a novel efficient attention mechanism consisting of efficient attention and frequency attention. The frequency attention mechanism utilizes a Laplacian pyramid to selectively emphasize each frequency information's contribution. Additionally, a parametric frequency attention fusion strategy is introduced to balance shape and texture features. The paper also presents a novel efficient enhancement multiscale bridge that effectively transfers spatial information from the encoder to the decoder, alleviating the drawbacks of traditional self-attention and surpassing its counterparts in medical image segmentation tasks. The proposed Laplacian-Former architecture, as depicted in Figure 1, integrates the efficient enhancement transformer block, a novel component designed to capture contextual information and recalibrate the representation space within an attention mechanism. This block initiates by applying layer norm to the input X, followed by the efficient frequency attention (EFATT) mechanism, which selectively incorporates various types of frequency information using the Laplacian pyramid to balance shape and texture features. Inspired by the importance of edges and textures in defining boundaries, the EFATT mechanism plays a crucial role in the architecture. To address the issue of reduced feature diversity in deep transformers, the architecture incorporates a diversity-enhanced shortcut DE method, which employs a Kronecker decomposition-based projection to insert additional paths with trainable parameters alongside the original shortcut X. This approach enhances feature diversity and improves performance while requiring minimal hardware resources. The output of the attention mechanism is then added to the diversity-enhanced shortcuts, and the result is passed through layer norm and mix FFN layers. This process is repeated multiple times, with frequency enhancement and patch expanding operations applied in between. The architecture concludes with a segmentation head, which outputs the final segmentation result. The use of EFATT and DE mechanisms enables the Laplacian-Former to effectively capture high-frequency details and enhance feature diversity, leading to improved performance in image segmentation tasks. The Laplacian-Former 5 is a crucial component of the frequency enhancement transformer block, utilizing efficient frequency attention (EFATT) to reduce computational complexity. This approach improves upon the traditional self-attention mechanism by adopting the method proposed by Shen et al., involving the softmax function on key and query vectors for normalized scores and forming the global context through key-value matrix multiplication. This efficient attention mechanism provides an equivalent representation of self-attention, alleviating issues of feature redundancy and computational complexity. Wang et al. Identified a significant limitation of self-attention mechanisms, demonstrating that they operate as low-pass filters, erasing high-frequency information and leading to a loss of feature expressiveness in deep layers. This limitation arises from the softmax operation, which favors low-frequency information containing shape information over higher frequencies carrying texture and edge information. To address this limitation, a novel frequency recalibration technique is proposed, which focuses on both low-frequency and high-frequency information. This technique involves constructing a Laplacian pyramid to determine different frequency levels of feature maps. The pyramid is built by extracting multiple Gaussian representations from the encoded feature using different variance values of the Gaussian function, as defined in equation 3. Each level of the pyramid contains distinct types of information, and frequency attention is introduced to efficiently aggregate features from all levels. Frequency attention involves multiplying the key and value of each level to calculate attention scores, and then fusing the resulting attention scores of all levels using a fusion module. The final frequency attention result is concatenated with the efficient attention result and applied with depthwise convolution to aggregate both information and recalibrate the feature map. Furthermore, the efficient enhancement multiscale bridge is proposed as an alternative to simply concatenating features from encoder and decoder layers. This bridge delivers spatial information to each decoder layer, enabling the recovery of intricate details while generating output segmentation masks. The approach involves calculating the efficient attention mechanism for each level and fusing multiscale information in their context. To achieve this, the query and value of each level are parametrized using a convolution, ensuring that all levels' embedding dimension is the same size. The proposed Laplacian-Former method is evaluated against state-of-the-art SOTA methods on the Synapse dataset for multi-organ segmentation tasks. Table 1 presents the results, where Laplacian-Former outperforms SOTA CNN-based methods such as R50UNet, UNet, AT-UNet, Trans-UNet, SWIN-UNet, Levit-UNet, Trans-DeepLab, High-Former, and F-Former. The Laplacian-Former method introduces a novel approach to incorporate global context into the feature representations. Specifically, the method multiplies the new key and value to attain the global context, which is then aggregated using a summation module across all levels. The resulting feature map is enriched by matrix multiplication with the augmented global context, followed by a linear layer to project the output to the same size as the encoder block. The experiments were conducted using the PyTorch library on a single RTX 3090 GPU, with a batch size of 24 and a stochastic gradient descent algorithm. The loss function combines cross-entropy and dice losses, with a base learning rate of 0.05, momentum of 0.9, and weight decay of 0.0001. The model was trained for 400 epochs. The Synapse dataset, comprising 30 cases of contrast-enhanced abdominal clinical CT scans, was used to evaluate the method. Each CT scan consists of 85 to 198 slices, with annotations for 8 different organs. The results demonstrate the effectiveness of the Laplacian-Former method in multi-organ segmentation tasks, achieving superior performance compared to existing SOTA methods. The Laplacian-Former's segmentation results on the synapse dataset are notable for their finer boundaries in the stomach and fewer false positive predictions for the pancreas, showcasing its superiority. Quantitative results demonstrate an increase in DICE scores compared to high-former and SWIN-U-net, highlighting the Laplacian-Former's superior learning ability. In skin lesion segmentation, the proposed method outperforms leading methods like TMU-net and SWIN-U-net, leveraging frequency attention for modeling local textures. The spectral response of Laplacian-Former also preserves high-frequency details, encouraging further exploration through supplementary visualization results. The paper introduces Laplacian-Former, a novel standalone transformer-based U-shaped architecture for medical image analysis. It addresses the transformer's inability to capture local context by developing a new design within a scaled dot attention block. The pipeline benefits from the multi-resolution Laplacian module to compensate for the lack of frequency attention in transformers. This design efficiently uses transformer architectures while keeping parameter numbers low. The performance comparison against state-of-the-art approaches on the ISIC 2018 skin lesion dataset shows Laplacian-Former achieving the best and second-best results in metrics like DICE similarity coefficient, sensitivity, specificity, and accuracy. Frequency response analysis demonstrates the effectiveness in capturing high-frequency components, highlighting the proposed approach's superiority over the standard transformer. Transformer-based models have emerged as a promising approach for medical image segmentation, offering improved accuracy and versatility. TransU-net, a pioneering model, employs transformers as encoders, demonstrating promising results in capturing complex patterns in medical images. The skin lesion analysis model takes this concept further, leveraging the transformer's ability to capture interscale dependencies, thereby enhancing segmentation performance. This is achieved through the hierarchical representation of features, which enables the model to effectively integrate information across different scales. Other notable models, such as high-former and misformer, have also been developed, incorporating hierarchical and multiscale representations to improve segmentation accuracy. These models have shown remarkable adaptability in handling diverse medical image segmentation tasks. Beyond these advances, self-supervised few-shot learning for semantic segmentation has been explored, highlighting the potential for annotation-free approaches. This paradigm shift enables models to learn from limited annotated data, reducing the need for extensive manual annotation. Throughout these developments, the transformer's versatility has been consistently demonstrated, showcasing its ability to adapt to various medical image segmentation tasks. Medical image segmentation has witnessed significant advancements with the integration of transformer models, specifically the contextual attention network and U-net. Researchers have modified or combined these architectures to enhance performance, as seen in papers like Laplacian-Former 11 and SegFormer. These novel designs prioritize efficiency and effectiveness in image segmentation. Other works, such as FATNet and Deformer, emphasize the importance of feature adaptability and dilated transformers for achieving better results. The attention-gated networks and efficient attention approaches focus on leveraging salient regions in medical images. These innovative transformer-based architectures have improved accuracy and efficiency in medical image segmentation. By adapting and combining different models, researchers have made significant strides in this field. The cumulative findings of these papers demonstrate the potential of transformer models in enhancing medical image segmentation, paving the way for further advancements. The Laplacian-Former model's ability to detect organs in the synapse dataset is evaluated using GradCam, a technique for visualizing attention maps. The results, displayed in Figure 4, demonstrate the model's effectiveness in detecting small organs, such as the gallbladder and aorta, showcasing its ability to learn local features. Moreover, the model successfully detects large organs, including the liver and stomach, demonstrating its capability to capture long-range dependencies. The attention maps generated by GradCam provide insight into the model's decision-making process, highlighting the regions of the input image that contribute most to the predicted organ labels. The Laplacian-Former model's performance in detecting organs of varying sizes demonstrates its robustness in learning hierarchical representations of anatomical structures. Furthermore, the model's ability to capture both local and long-range dependencies is attributed to its novel architecture, which incorporates graph Laplacian operators to model spatial relationships between image regions. This design enables the model to learn a more comprehensive representation of the input image, leading to improved organ detection performance. The results presented in Figure 4 support the author's argument that the Laplacian-Former model is a promising approach for medical image analysis tasks, particularly in detecting organs with varying sizes and spatial relationships. The Laplacian-Former model's performance in skin lesion segmentation is visually compared to ground truth boundaries in Figure 5, where green denotes ground truth and blue represents predicted boundaries. This figure demonstrates the model's capabilities in segmenting skin lesions from input images. However, Figure 6 highlights the model's pitfalls in skin lesion segmentation tasks. While the model can capture possible lesions even when annotation is lacking, as shown in the first column, it struggles to accurately capture boundaries, despite performing well in capturing local texture, as illustrated in columns 2 and 3. Furthermore, the model achieves accurate results even with coarse annotation, as seen in the fourth to last column. These visual comparisons provide insight into the Laplacian-Former model's strengths and weaknesses in skin lesion segmentation tasks. The results suggest that the model is effective in capturing local texture and possible lesions but may require further refinement to accurately capture boundaries. The analysis of these pitfalls sets the stage for future work in improving the model's performance in this task.